Thank you very much, everybody, for being here and for Omololu for inviting us. We're very excited to be here and teach you all about AFLOW. My name is Marco Esters. I am part of the AFLOW team here at Duke University, and with me are Frisco Rose, Professor Frisco Rose. He's an assistant research professor with us here at Duke University and the Center for Autonomous Materials Design. Dr. Koriosis, he is a postdoctoral associate at Duke, just like me, and Professor Cormac Tor, who is an assistant professor at the University of Texas in Dallas, and is also one of the directors of the Center for Autonomous Materials Design, and who isn't here, but he's our boss and another director of the Center for Autonomous Materials Design, Professor Stefano Cutarolo. He started the entire AFLOW project that we are all part of and that we are excited to talk to you about the next 4 days. I'm sure you've all had enough Zoom meetings to last at least a lifetime, but just to recap a little bit about logistics, please be muted unless you're speaking. That's just makes everything a lot less disruptive. And if you have a question, feel free to just post it in the chat or use the raise hand function that you find under reactions. And then you just click the raise hand button and we will see it in the chat and we will be able to answer your questions, and then you can unmute and just ask your question. You'll see that right here. So what are we doing? We are trying to find new materials for applications that are important for industry and academia. But what kind of materials, what kind of properties are we looking for? We're looking, for example, for thermal barrier coatings that can be used in energy applications, aerospace, for example, in turbines or in coatings for any kind of airplane or spacecraft. We're looking for super hard and wear resistant coatings, for example, for machine tools in industrial applications. We are looking for any kind of biocompatible materials that are corrosion resistant. For example, alloys for medical implants. I think most of y'all have heard about these titanium screws for broken bones. We were looking for better materials than that. Then a big area of research is photovoltaic materials for solar energy harvesting to get away from fossil fuels for to prevent or to limit global warming that we're experiencing today. And another side of that coin is energy storage, solid state electrolytes, lithium ion batteries, and another very constantly important application of superconductors and heat sinks for advanced electronics. Both of them very, very important for what we're doing, which is computational material science, and also for energy applications that we very desperately need to meet our energy needs. The challenge for this to get there is that we just have a vast material space. If we're just looking at these elements here, which are viable in materials, they're marked in blue, and we're looking at just the element combinations that are possible. We're getting for binaries to 3,000 element combinations, which sounds manageable. With the more elements we combine and with the rise of high entropy materials, using materials with 5 or 6 components is something we need to look into. We're getting to a combinatorial problem that becomes increasingly intractable, especially for experimentalists. Here for 6 components, just combining all the elements, we're getting to more than 250 million combinations. And that is just element combinations. If we're looking at different structures, here's just a very, very small subset of possible structures that we can have. We are quickly getting into, we're just selecting a few of them, we're quickly getting into a space of 10 to the power of 177 different potential structures that we can look at. For an experimentalist, this is impossible to do because experiments take a long time and your experiments may fail for reasons that, for a lot of reasons, even though your material might be synthesizable. What we're doing is we do automated computational materials discovery. We are starting from experimental structures or structural prototypes, the latter of which we'll be talking about tomorrow. We use automated quantum mechanical calculations. AFLOW primarily uses VASP using densital functional theory. Then we have a database where we store all the results, which we will talk about today. And we do post-processing, determine properties, and identify maybe potential candidates for you all. We'll be interested to see how we can use these materials to feed into machine learning models or maybe build our own. AFLOW itself does more or less a wrapper around DFT code, but it does a lot more. It does it generates input files for DFT, but also does post-processing. And our workflow is the following. We generate our input files, do DFT calculations, and we also manage these calculations. Sometimes calculations go wrong for a lot of reasons, and it is important for such a high throughput framework to actually see that it went wrong and also figure out what to do about it. So we have automatic error corrections, and then we redo the DFT calculations based on these potential fixes. Afterwards, we calculate our properties once the DFT calculations are done and store them in our database. AFLOW source is open source. It is available under the GPL3 license at this link here. You should have that on your slides. We also have a web portal where we show where we have all our properties listed too. We have currently about 3.5 million entries, and all that results in about 700 million calculated properties. And we show a select set of properties, but we have a lot more. We have formation enthalpies, band structures, charges, and thermomechanical properties in them. And we have about 150,000 quaternary systems, so element combinations with four elements calculated. We will today focus mostly on our web features in the entire session here. But we also have more. We have an entire command line tool. And if you are interested in learning more, we have some schools and seminars that you can look into. What we'll be focusing on the next 4 days are 5 web applications. Today, we will be talking about the search application. Tomorrow, I will introduce the prototype encyclopedia and also our online features that have select AFLOW functionality in a web interface, so you don't have to install our program. Corey will talk about AFLOW Chal, and Cormac Professor Tor will talk about the AFLOW machine learning application on Thursday. As I said, AFLOW is a very big autonomous calculation code. It can do a lot more, and we unfortunately will not have the time to talk about this in the 8 hours that we have this week. You can install AFLOW yourself to look more into use it in your command line environment. We have it available for Linux, Mac, and Windows. They run natively on Linux and Mac. On Windows, you need additional software, but we have a link here where all these steps to install it are listed in aflow.org/install-aflow, where you can install the AFLOW command line tool. You don't need it for our session here, where you do everything in a browser or using Python. But if you are interested in learning more or using it more, this is the way to install it. We also have seminars that are not related to AFLOW, but are just scientific seminars about material science. We have experimentalists. We have computational people. The next one here is David Broider. These seminars are free. You can sign up. They are typically at 3 p.m. Eastern US time, which is 10 p.m. currently Rwanda time. Starting in March, it will be 10 p.m. It will be 9 p.m. But they're free. You're free to sign up. The link is aflow.org/seminars. I encourage you all to attend. As I said, they're free. And we have very great scientists. Last week we had John Perdue, and the next one is David Broido. So feel free to check out that link and join our seminar series. We also have we have AFLOW schools just like this one here, but we also have extended ones. We typically have one every year with the Texas A&M that are much longer and talk about all AFLOW features. For example, the symmetry that we're going to talk about tomorrow has a lot more capability with the actual AFLOW software, but you are also free to sign up for AFLOW schools once they're available, and they are also typically free. So you feel free to sign up there and join us there. If you are interested in hosting AFLOW schools, please contact Professor Stefano Cortarolo at this email address that you also have in your slides. If you want to get added to the waiting list for future schools and get an announcement when they're happening, feel free to go to aflow.org/seminars and sign up for the waiting list. At last, we are currently looking for postdocs. We have multiple openings for postdoctoral associates using autonomous property predictions and high entropy ceramics. The link is also on your slides. Feel free to check out the job posting and contact us if you're interested and apply. That concludes the advertising section. We are currently just going through a brief outline what we're going to do in the next 4 days. Today we have Frisco Rose talking about our database and how to interact and search for our data using graphical user interfaces and APIs. Tomorrow it will be me again, talking about symmetry and prototypes and structure comparison, which are very important structure analysis tools that will be helpful for machine learning. Then on Wednesday will be Coriosis, who will be talking about convex hulls and how to determine synthesizability and how to correct DFT energies, which for certain materials are not very reliable. And then on Thursday, Professor Cormac Torr will talk about our machine learning applications and our machine learning models that you can use for your own structures and materials. And at the end, we will also have a Q&A session when we have time to answer all your questions that may have come up in the next 4 days. And with that, I will hand over the baton to Frisco Rose, who will be talking about our database and our search functionality.